Welcome to the Forensics and Inverse Camera tutorial. In this tutorial, we describe control points, inverse camera, checking results of an inverse camera, using the epipolar line in referencing, doing displacement measurements, and evidence markers. The forensics tutorials will work through examples of crash and road scene projects. The first example will be a vehicle crash project. We will determine crash measurements on a vehicle using photographs taken from an unknown camera. To be able to do this project, we first have to get some known coordinate information about points on the uncrushed part of the vehicle. We can find this known information or control points in an identical exemplar or undamaged vehicle. This exemplar vehicle is surveyed to extract 3D coordinates to be used as control points, which are needed by Photomodeler's inverse camera to solve for the unknown camera parameters. In this case, Photomodeler was used as a surveying tool to extract the 3D coordinates from the exemplar vehicle. The data was then exported as a 3D DXF file. We start a new project by clicking the New Project button from the toolbar. We choose Standard Photomodeler Project and click Next. We review the project steps and click Next. We choose a unit of inches and an approximate size of 192. We click Next and choose an unknown camera for inverse camera forensics. We will be using two photographs of a crushed Toyota Corolla taken with an unknown camera. We click Next and enter the camera name Unknown Crush Camera. We click Next and choose No, this camera only uses one focal length. We click Next. We know the photos came from a 35mm film camera. We choose this option and click Next. We were provided the scanned digital images and do not have the image prints. If we did have the image prints, we would choose this option and the camera wizard would go through an extra step to account for possible unsquare pixels. We pick digital image files and click Next. This pane reminds us that the wizard is assuming the camera has square pixels. We click Next. We don't know what the focal length is, so we will leave it at the default estimate of 50mm. This number will be adjusted by inverse camera during processing. We click Next and review the initial set of camera parameters. We click Next and click Add Remove Images. In the Forensics folder, we select the two images CoreCrush1.jpg and CoreCrush2.jpg and import them. We click OK, and we receive the inverse camera message telling us we have assigned inverse camera to photo 1, and the focal length flag has been set. This means the focal length option in photo 1 properties is set to be solved for when inverse camera processes. We click OK and get a second message. This one tells us that an inverse camera description cannot be shared by two photographs. Since we do not know anything about the photos, we cannot assume that they were taken with the same camera or at the same focal settings. This message tells us that a copy of the camera description has been made. We now have two cameras in the project, each assigned to a separate photograph, allowing them to be solved for independently. We click OK, and the images are included in the project. We click Next, then Finished. The project is now set up, and the screen opens with the two photos in the sidebar. We open up the two photographs. To process projects like this with 2 or 3 unknown photographs of a forensic scene, such as this crushed vehicle, or an accident or crime scene, we need to use constraints. In this project, we will use the constraint called control points. The control points help in solving for the camera parameters as well as providing data for the model. To add the control points, we select Marking, Mark Control Points mode. This brings up the control point dialog. We click Modify, and quickly delete the default control points. We click OK, then Import. We are going to import a 3D DXF file. The units are in inches, and we choose Do not adjust these controls to ensure that the control point coordinates are not adjusted during processing. This is suitable when you will mark a low number of control points. We click Browse, and select the Corolla exemplar.dxf file, and click Open, then OK. The control points are shown in the list view of the dialog. We click the 3D view option and get a full 3D view of the control point data. we can see that we have a fairly detailed model of the undamaged exemplar Toyota Corolla. This model actually contains more detail than is normally required for a control point project, but this detail will help demonstrate aspects of this project later in this tutorial. These control points were created in a separate photo modeler project. That project used a calibrated camera and 6 photographs taken from a good variety of angles. This ensured a strong result and therefore a good set of control points, which in turn increases our chances of a good inverse camera result. Control points can also be created using traditional surveying instruments. Any method that can be used to generate an accurate set of 3D coordinates can be used as a source for control points. Another technique for unknown photo projects, when the control data comes from another photo modeler project, is to combine the projects. For example, you would first complete a photo modeler project of the exemplar vehicle using a calibrated camera. The points in the project can then be changed to be fixed by selecting all the points in a point table and choosing the Fixed option in the Point Properties dialog. Fixed points are used the same way as control points with respect to an inverse camera project. You then import the 2 unknown photographs and assign them an inverse camera. With the images imported, you can then reference the fixed points to matching points on the crushed vehicle photos. When you process, inverse camera will use these fixed points to solve for camera parameters. Further details on this method can be found in the help file. In this tutorial, we will use the control point file import method as it is more flexible. We click the List View option. If we scroll the list, we can see that all the points have ID numbers, but there are also a few points that have unique names. The ID names come from text entities in the DXF file. These particular points have been named to help us identify the points more easily when we mark the control points on the photos. For example, point 107 has ID name DS Front Rail, which is short for the front part of the rail molding that runs down the driver's side of the car. We move the dialog off to the side so we can see Photo 1. We activate Photo 1, and our cursor changes to control point mode with a triangle and dot on the end. We select point 107 and move the cursor into the photo window. We use Alt-Zoom for a closer look, then mark the point. Next, we select point 109, using the ID name as a clue for its position, and mark it here. We scroll to point 135 and mark it here, by the rear of the driver's side door. We scroll to point 34, named for driver's side B-pillar, top of the window, and mark it. Next, we mark driver's side B-pillar bottom window. It is very important that we mark these control points in the correct corresponding positions. This is why it is important to give the points in the control point file a unique name that will help you find the correct position it corresponds to. Incorrect or inaccurate control point marking will result in poor results when inverse camera processes. It is very important that the control points have good coverage on the photo. You want to try and have control points marked across the photo, rather than all bunched in one area. Especially when solving for focal length, you will also need some points with varying depth, otherwise you will get poor results or inverse camera will not solve at all. All our points so far are covering this one plane of the driver's side. Point 3, whose name is short for passenger B-pillar bottom window, and point 6, passenger side C-pillar bottom window, represent points on the other side of the car. These can be viewed through the windows. We mark these 2 points. We now have some better depth coverage of the photo. We move the Photo 2 window over to the left side of the screen. We will mark control points on this photo as well. We mark some of the same control points that could be seen on Photo 1 as well. Point 39, driver's side windshield bottom, is actually hidden behind the damaged fender. It is not a good idea to try and guess the position of control points because an inappropriate position will negatively affect the project results. We skip this point. We mark point 3 on the passenger side. The point 40 ID is short for driver's side key. Point 42 gives us more depth coverage of the photo. Points 49 and 57 cover some points on the driver's side passenger window. Point 73 is a point on the windshield. This gives us a good set of control points on our photos. We start this segment using the controlmark.pmr project from the Forensics folder. We have the two photos and a photo table opened and tiled. The photos have all the control points marked in the appropriate positions, but there's been no processing yet. The photo table shows the two inverse cameras and their default parameters as set up in the camera wizard. Next, we will process and inverse camera will solve for the camera parameters. We open the process dialog. The important part here is to look at the options section. The first step is orientation, with inverse camera in brackets. When the photos have constraints or control points marked for inverse camera processing, this stage has to be done. In this case, since the photos are not oriented, this option is on by default. In other cases, when processing has already been performed, you may wish to redo the inverse camera processing. You can then choose the Orient All Photos option. We click on the Steps tab. Processing will go through the first two steps: orientation of two photos and global optimization. We click Process. The project processes successfully and we click OK. We look at the photo title bars and they now indicate they are oriented. The photo table shows changes in the camera's focal length. Each of the photos has solved with a different focal length. In certain cases, you may want to solve for the principal point. This may be necessary if you think the photographs have been cropped and images off-center. Solving for principal point requires a very strong set of control points with good coverage and depth on the photo. It is a good idea to start by solving for focal length only first, and check your results. There are a number of quality checks that we will go through in a few minutes. If you go through these checks and still find that there are some questionable results, then you can try inverse camera processing with principal point as well. To set this up, right-click over the photo and choose Photo Properties. In the Inverse Camera Processing section, choose the Principal Point option. The Format Aspect Ratio option is not used often in solving inverse camera, and is only important when you suspect there is a scanner error or some other problem that would affect the squareness of the pixels. We close the Properties dialog. We will now demonstrate the techniques used to determine the quality of the results of the inverse camera processing. First, we look at the focal length values and ask ourselves if these numbers appear reasonable. It started at a default value of 50 millimeters, and inverse camera processing adjusted them. These numbers appear fine. We close the photo table. The next check we do is with projections. We click the Projected tab and choose Control Lines. We can see the control point file that we imported projected onto the photographs. We change the settings for a better view. We click the Settings tab and adjust the transparency bar towards solid. We study the photo to see how well the control file model matches the vehicle in the photo. The marked control points have been used to lock the rest of the control file in place, as shown here in this pinkish color. Of course, the projected lines in the front area will not match the crushed area in the photo, but the uncrushed area should match correctly. We check how well the lines match up along the windshield, windows, and doors, and everything seems to line up well. In Photo 1, we are able to visually compare the crushed vehicle and the exemplar model. We can see the change of shape and the effect the impact had on the front of the car. The next check we will do is a review of the marking residuals. We open a point table and choose the quality configuration. We sort by largest residual. The largest residual is close to 9 pixels. In a regular photomodeler project, using a calibrated camera, a residual this high would not be acceptable and would indicate a problem. In an inverse camera project, residuals can be judged differently. In this project, we are solving for the camera parameters using control points that are set so their coordinates cannot be adjusted, and we are not 100% sure they are marked in the exact correct position. This results in higher point residuals. For these types of projects, residuals around 10 pixels are still acceptable. When they start to hit 15 pixels and above, then you should review your control points to see if they are positioned correctly. The residuals in this project are acceptable, so we close the point table. Next, we will go through a method for checking quality using referencing. First, we will turn off control lines from the projected tab. If the photo is oriented well and the solved camera parameters are good, then we can use the referencing tool to verify that positions of newly marked points match up. We zoom in on this window of the car in the background in both photos. We click Reference from the toolbar, and the Reference toolbar appears. We click the Mark on Source Photo icon. This tool allows us to mark a single point on the source photo, then move our cursor over to the destination and immediately reference it. We mark a point at the cross of the T that is written on the window. A mark appears and we move our cursor into the destination photo window. The reference helper line, also called the epipolar line, appears. We can see that this line goes through the section we marked. The reference helper line helps us find the intersection where we should mark the matching point. We mark the point at this intersection. We will try this with another point. We mark this T on this other window, and we can see the reference line properly intersects the matching area on the destination photo. If the reference helper line appeared off target, such as over here, then this is an indicator that the project results are poor. If this was the case, then we would have to review the placement of our control points and review whether we have good coverage across the photo. We mark the point. You should also be sure that the exemplar vehicle from which you got the control points from is the exact same model. It should be the same make, year, and model. Even some of the minor features such as body lines and molding can vary in shape or location in the same models due to dealer options and production variations. Similarly, with a road scene, you should be careful that features you are surveying for use as control points have not been moved since the time of the original photographs. The survey of control points is usually done after the fact, and you want to be sure that you are getting the coordinates for the objects that were in the same position at the time the original photos were taken. Finally, we will open a 3D viewer and look at the camera station positions. We open a 3D viewer with points, lines, and camera stations turned on and click OK. We maximize and do a quick check using the viewer controls. The camera stations look fine. We close the 3D viewer. We have performed our quality checks and we are satisfied with our results. We can now move to the next step, which is marking and referencing of points on the damaged section of the car. Once the inverse camera photos are solved for, then we can continue with the project as normal. We click Window Tile and Window Zoom to fit all. We use Zoom Photo Area to zoom in on the crushed sections in both photos. On Photo 2, we use the Point tool to mark some points on the front of the crushed hood, some in the drill holes, and on parts of the bumper and undercarriage. We select those points using the Select tool and dragging, then click Reference. Photo 2 becomes the source photo, and Photo 1 is the destination. We move the cursor into the destination photo and use the epipolar line to help us mark the points. The line looks to be close to the right place for matching up. If the line is slightly off, we are not concerned. We reference in the correct place, and when we process later, the project will improve somewhat. If the epipolar line was not close, then we would have to review our project so far and try to improve it. We reference the points using the Alt Zoom for better accuracy. Now that we have these new marked and referenced points, we will reprocess. We are satisfied with our inverse camera solutions, so there is no need to choose the orientation or inverse camera option. If we were not satisfied, we would choose Options and choose to reorient all photos. We will just do the global optimization. This will include the new points, and they will factor in processing and should strengthen the overall project. We click Process. It processes successfully, and we get a slightly smaller final error than we did in our first processing. We click OK. Our final goal in this project is to get displacement measurements from a profile of the interior bumper shown here. The plastic covering of the bumper has fallen off, so we will use the inner bumper as our source for crush information. We use Image Enhance for a better view of the bumper in Photo 2. We go into Reference Mode and choose the Mark on Source Photo tool. There are not many distinct points to mark and reference along the bumper edge. We will mark a point along the top edge of the bumper near some other identifiable feature, so we have a general idea of its location when comparing to the other photo. We then move the cursor over to Photo 1 and use the epipolar line to help find the matching position. The line intersects the bumper here, and that is where we mark the point. We do a quick check to see if the identifiable features are in the approximate locations across the two photos, and this appears to be correct. We mark some other points along the bumper, using visual clues where possible. Here we mark a point at the top of this scrape, and reference it with the help of the epipolar line. We then use the Line tool to join the points and we have created the initial profile of the bumper. We start this segment with a project called done.pmr, found in the Forensics folder. We open Photo 1 and review the points around the crush area. The bumper has been modeled in more detail, while some points have been added along the hood for a more complete model. We open a 3D viewer with points, lines, and control lines. The points and lines represent the points in our project, including the control points and bumper points. The control lines represent the control file, and in an oriented project they can be viewed in the 3D viewer. We click OK and maximize. We have a top-down view of the marked data and control lines. The pink lines represent the control file, while the white points and lines show the data we marked. The control file also shows this extra line that has been added at the level of the bumper. This line was added so we will be able to do profile measurements. This extra line can be added to the DXF file using a CAD package or in a text editor in some cases. We hit Reset to go back to the top-down view. We zoom in on the front area. We want to get displacement measurements from this line to these bumper points. There are a couple methods for doing this. You can do certain measurements right within PhotoModeler, or you can export the model to a CAD program. If you're using a technique where you want equally spaced measurements on your crush profile for doing your delta V calculations, it might be easier to export the crush project data to your CAD program in the form of a 2D DXF file. You can compare with a 2D DXF profile of the exemplar vehicle and do the equally spaced measurements within the CAD program, or even on a plotted drawing. To do the measurements in PhotoModeler, we go into Measure mode. We grab the Measure toolbar so it is in a floating position. We select the control line, press Shift, and select this point on the bumper. A distance of 12.9 inches is displayed in the Measure dialog. This is a straight displacement, representing the closest distance between the point and the line. We do a few more displacement measurements between the bumper points and the control line. This displacement measurement is 14.2 inches and 17.8 inches and 22.8 inches. and the last point is displaced 27.5 inches from the control line. This concludes the crush measurement project using photos from unknown cameras. We are able to complete a project such as this through the capabilities of control points and inverse camera. We demonstrated how to view the control data and project it onto your photos, how to check quality of the inverse camera results, and how to do the measurements in PhotoModeler. EOS Systems and your local photo model dealer sell specially manufactured evidence markers. These are rigid plastic objects designed by EOS Systems specifically for use with PhotoModeler. There are 20 markers in a set. Each marker has a large letter on the lower half so they can be easily identified across photographs. There is also a white circle on the top portion for easy marking. The letter and dot contrast well with the black background for maximum visibility. The evidence markers can be laid out at accident and other forensic scenes where you are taking photographs using your own camera. The markers provide highly visible points that can be marked and referenced across photos and help produce accurate diagrams. The markers can also be used at night as they are designed with a special reflective material that is visible at night when using a flash. The letters and dots on the markers can be seen in night photos up to distances of 200 feet. In this demonstration, we have a road scene with a skid mark and some evidence markers placed on the road. Here we see a close-up of the J marker with a dot for marking, and we can also see the skid marks on the road. There are 8 photos in the project. We turn on points and lines in the Mark tab to show the data we have marked on the photographs. The 3D view shows the top-down view of the final result, with the skid marks, the edges of the road, stop signs, evidence markers, and so on. We rotate it in the 3D viewer for a different view. Here we have 2 3D viewer windows, one with a top-down view and one with a front view. Typically, at the end of a diagramming session of a road scene in PhotoModeler, you would export the data as DXF into a CAD package such as AutoCAD, AutoCAD Lite, AutoSketch, or Crash Zone. You would then complete the diagram using additional features to produce a scene diagram suitable for use in presentation in court. This concludes the forensics tutorial. We have worked through topics of control points, inverse camera, checking results of inverse camera, marking and referencing using the epipolar line, displacement measurements, and PhotoModeler evidence markers.